Okay, continuing on from yesterday, this is 1-4 day 2. We got g of g, which we're composing g inside g. So keep in mind we're going to put the square root of x inside the square root of x. So we place that in, and I got x to the 1/2 power to the 1/2 power, which becomes x to the 1/4 power. Now this is an even root, so it's good for anything positive is 0, so my domain is 0 to infinity. If it was an odd root, we could have gone from negative infinity to infinity. Now, there are times in calculus where we need to reverse the composition process. So this is the decomposition of functions. Now, you got to be aware, there is often more than one way to decompose a function. So decomposing functions. For each function h, find functions f and g such that h of x is equal to f of g of x. Now, keep in mind, make it the easiest you can. If you notice that I have x plus 1 inside a squared and x plus 1 inside a 3 times something plus 4, hey, make it as easy as possible. So as we do this, say g of x is x plus 1. Okay, so then f of x becomes x squared minus 3x plus 4. So you're just taking out the x plus 1. Now, give it a try over here for yourself. Make it as easy as possible. Okay, so now we have this function. We're going to take g of x. Well, if g of x was x cubed plus 1, it'd be pretty darn easy. So g of x is x cubed plus 1, and f of x is the square root of x. You could, I've had people do some funky stuff with different things. Hey, g of x could have been x cubed minus 2, and this f of x could have been the square root of x plus 3. But remember, if I'm asking you to do a decomposition, make it as easy as possible. Have you seen this porcupine? His name is Pokey. If you see him, please contact Mr. Anksman. Mr. Anksman is apparently missing Pokey. Now let's apply our knowledge of compositions. Modeling this function, composition. In the medical procedure known as angioplasty, doctors insert a catheter into a heart vein through a large peripheral vein and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate as 44 cubic millimeters per second. So remember, the sphere volume is 4/3 pi r cubed. Okay, so now find the volume after t seconds. This is v of t, the volume after t seconds, by the way. So now we have 44t because we have, suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. So that's where that came from. When the volume of v, what is the radius r? So I have the volume with respect to r is 4/3 pi r cubed. So now we're looking at this. We got 4/3 pi r cubed. We're solving for r. By the way, I'm dropping the in terms of r, okay, from the v, make our calculations easier. I multiply by 3 on both sides, divide by 4 pi, and I have r cubed. So I multiplied by 3 over 4 pi to get to this point. And this is equal to r cubed. Now I've got to take the cubic root. Okay? So r is equal to the cubic root of 3v all over 4 pi. So now r in terms of v, with respect to v, is the cubic root of 3v over 4 pi. Now, write an equation that gives the radius r as a function of time. What is the radius after 5 seconds? So now I've got r with v with respect to t. So I'm going to plug in where I see v at 44t. Now this is that r down here, and I'm grabbing that 44t, bringing it down, and using that composition idea of the function to make this work for us. And now I can pop in and say, hey, 33t over pi, because I divided out a 4 out of here. That's 4 times 11. 11 times 3 is 33. 4 is drop out, and that's where I'm coming from. Now I get to find out what is the radius after 5 seconds. So now the radius after 5 seconds is 33t, and where t is going to be 5 here, pi. So now I pop that in. and I find out that it's going to be 3.74 millimeters. Okay, so we've answered this as talking about the modeling with function composition. So we've got that kind of set up as we step through, and we know our radius for our angioplasty. Now you try, you're buying your first semester college textbooks. The bookstore is offering a special deal for this week only. You can use a coupon for $10 off of your book and the in-store discount of 10% off your total purchase. Now you can, and the best part, you get to decide the order in which the discounts are taken. Doesn't matter. Let P equals the purchase price, D of P, final price using the 10% discount, and T of P, the final price using $10 coupon. So we have this, D of P and T of P. So we have this as percent off. So if I take the 10% off, that's 0.9P. And here, the T of P, P minus 10, that's like $10 coming off the price. Now there's two ways they want us to consider. They want us to look at the price with T of P, taking the $10 off, and then taking off the percent, or taking off the percent and then taking off the $10. So the first one, taking off the $10 first, taking off the $10 first, and then taking off the percent. Okay, so we've taken off the $10 and we're taking off this percent. Or the second one, we take off the percent and we take off the $10. Which is more? Or which is a better deal when we consider it? Well, when we consider it, 0.9P minus 9 and 0.9P minus 10, take the percent off and then take off the $10 is the better deal. The better deal is to take the 10% off first, then use the $10 coupon, C of T. So C2 is the better deal. Okay, so moving on. Relations and implicitly defined functions. There are many curves in mathematics that do not pass the vertical line test. That's what VLT is, vertical line test, and are therefore not functions. Equation of a circle is one of them. However, there is often still useful geometric and or algebraic relationships between the point xy on the graphs. The general term for a set of ordered pairs xy is a relation. If the relation happens to be a single value of y to each value of x, then the relation is also a function, and its graph will pass the vertical line test. In the case of the circle with equation x squared plus y squared equal 4, both 0, 2 and 0, negative 2 are in the relation, so y is not a function of x. So we can't graph it with our calculator, but if we pair our relationships differently, we can, okay? Now before we get there, let's talk about pairs in a relation. Determine which of the ordered pairs 2, negative 5, 1, 3, and 2, 1 are in the relation defined by x squared y plus y squared equal 5, and whether the relation is a function. So let's talk about, the situation with the different values. Okay, so each value, I'm going to just pop in my x's, pop in my y's. Okay, now 5 is equal 5. Okay, it's in the relation. Now here I put in 1, put in 3 here, and I determine that it's not in the relation. Here if I put 2, 1 in, I put in and find out that it's in the relation. Now be careful, 2, 1, 2, negative 5. Now this situation is a situation in which I have two different y values for the same x value. Okay. So since 2, negative 5 and 2, 1 are both in the relation is not a function. Two y values for the same x value are my output. So now let's go back to considering the circle. When I consider the circle x squared plus y squared equal 25 and solve this for y, what two equations do I get? Well, I subtract x squared from both sides, and then I take the square root of y squared and the square root of 25 minus x. Well, I get plus or minus the square root of 25 minus x squared. it's important to keep in mind that since I will have two y values for every x input, these will not currently be a function. But if I split my y values on my graph, I can actually graph a circle. I can graph y equals the square root of 25 minus x squared in y1. And in y2, I can graph y equal negative the square root of 25 minus x squared. This will give me the two versions of my graph. So for an example, if I graph the first, the square root of 25 minus x squared, this will give me the top half of my graph. And then if I graph y equals negative the square root of 25 minus x squared, it will give me the bottom part of my graph. If I graph them both simultaneously on my graph grid, this is what it'll look like. I'm hoping your graph will look much better than this with my drawing skills, or the lack thereof. So keep in mind, this is known, since the ordered pairs in either of these functions satisfy the equation, we say that the relation given by the equation defines the two functions implicitly. We just split it up, and we're able to graph the two equations separately. And separately, each equation is a function, but together they are not. Okay, so now, using implicitly defined functions, describe the graph of the relation here. Now, we've got this hint, the factor and solve for y. Well, this is an x squared, this is a y squared. I'm going for x plus 1 y squared to see. Okay, so we got that. Let's just double check. X times x is x squared, xy is 1xy, and xy again. So it's 2xy and y squared. So that's what we'd get if we actually factored our original equation. Now, if I take the square root of both sides, I get plus or minus 1 on the right. And this time, I'm going to solve for y. Remember, when I do this implicit defined functions, I've got to solve for y so I can put it into my calculator and graph the two functions. So I've got one function with y equals negative x plus 1 and y equals negative x minus 1. Okay, so I can graph the two things just like this. And if I do it on a grid or if I do it on my calculator, I'll have parallel lines going through here. Okay, so y equals negative x plus 1 and y equals negative x minus 1. So using implicitly defined functions, describe the graph of the relationships here. Well, I'm describing the graph, so this is my graphs and they're two parallel lines. Well, your homework for today is day 2, 21 to 30, 31 to 43 odd, and 45 to 50. Continue working on yesterday's homework, and we'll talk to you soon. Have a great day.